So now that I've talked about condition variables as an abstraction and shown you some of the key moving parts and a little bit about the protocol of how you have to acquire a lock and check a precondition and so on in a loop, at long last we can turn our attention to the Java ConditionObject, which of course is an implementation of condition variables. So condition variables are the abstraction. They've been around for many, many decades. Java has a condition object that implements that abstraction. And interestingly enough, this particular class is actually nested inside of the abstract queued synchronizer class. So it's kind of hard to get to on its own right, but as you'll see, you rarely ever need to define one directly. Instead, you're going to use a factory method defined on reentrant lock to get you a condition object. The condition object class implements the condition interface. And a good thing to do is read the condition interface. It gives you some interesting insights as to how it works. Under the hood, the condition object is nested within the abstract queued synchronizer. Abstract queued synchronizer is this very powerful framework that's used by many of the other synchronizers in Java that require FIFO access to shared state. And so condition object is nested inside of it. That's the little nesting sign in UML. And then a condition object, as we'll see in a second, basically is a doubly linked list of nodes. And this doubly linked list of nodes is used to provide a wait queue or a wait set for the threads that are blocked, awaiting their chance to see if the condition that they're waiting for is now satisfied. And you can read more about the abstract queued synchronizer framework if you're curious about it here in this paper by Doug Lee. So the set of threads, which is the wait set, use this to coordinate their interactions. And they do that by selecting the order and the conditions under which they run. If you think back to our discussion about coordination, we talked about coordination being focused on having threads run at the right time, under the right conditions, and in the right order. So that's what this type of synchronizer is all about. It's about coordinating the interactions of the threads, in conjunction, of course, with a mutex for mutual exclusion. A condition object is always, always, always used with some lock, almost always Java reentrant lock, which we've talked about before. And this lock protects the shared state in a condition expression from concurrent manipulation. So it can't be modified accidentally while it's being checked in that condition. The way you actually get the condition object is by calling the new condition factory method. So that returns a condition object. It returns it as a condition, but it's a condition object. And that also, of course, associates that condition object that comes back from this factory method with the reentrant lock upon which it was called. Now, one of the things we'll see later, and it's kind of interesting, you can actually have multiple condition objects sharing the same lock. So we'll see that when we talk in more detail about array blocking queue and its implementation. It actually shares those things. Now, interestingly enough, both reentrant lock and condition object instances have internal queues, but they're used for different things. So the reentrant lock has a queue that queues up the threads that are waiting to acquire the lock. So if you have, for example, something that's in fair, if you have the fair synchronizer version, then semantics of reentrant lock, that you're going to have this queue, and it's going to be used to queue them up in order. Likewise, condition objects also have a queue, and they have a queue of threads that are waiting for some condition, or some conditions, if you have a queue of threads, to become true. So there are two different queues, and you'll see when we start talking about the methods in condition object later that when you signal a condition object, what that does is it takes the thread that's next thread that's waiting, and it moves it from this wait queue to the reentrant lock's wait queue. And we'll talk more about that when we get to that. It's possible to have multiple condition objects per Java object. So an object that you implement or a class that you implement as a programmer can have more than one condition object. So for example, the array blocking queue that we'll look at shortly has both a not empty and not full condition in it. So you can have two conditions. And this is important because it allows you to be able to have more sophisticated and more efficient means of coordinating multiple threads. And as you'll see with not empty and not full, you can have two different types of threads that are waiting for the queue to be not empty and threads to be waiting for the queue to be not full. And they can both be waiting separately. And that allows you to have more efficient signaling and more efficient coordination between the different threads. As I mentioned before, you can have multiple condition objects sharing a single lock. Now, what's interesting about this, and this is why it's important for the case of the array blocking queue, putting and taking things in and out of the queue, at least with the array blocking queue implementation, share common state, like the count, for example. And so as a consequence, they both have to share the same reentrant lock just because of the way they're implemented. It's also possible to implement queues where you can have different locks protecting different parts of the queue. So you can have one lock that protects the head of the queue, one lock that protects the back of the queue. And so for other kinds of queuing implementations like link blocking queue, where you can efficiently put things at the front or the back and efficiently take things from the front or the back, we actually have multiple reentrant locks, 2 in this case, and multiple conditions. So it all depends on the implementation, what the association is between the condition object or objects and the reentrant lock or reentrant locks. And that's pretty cool, actually. As a contrast to user-defined applications of condition objects, Java's built-in monitor objects always only support one monitor condition. So there's only a single wait queue on a built-in monitor object. There's only one. So with user-defined classes that you write, you can have as many of them as you want. This one has 2, for example. But if you're using the built-in monitor objects, they only have one. And that is actually quite a limitation. So we'll talk more about this when we talk about Java's built-in monitor objects later in the course. But it's kind of a pain. And the reason it's a pain is because you end up having to use the notify all method quite a bit, because you'll have groups of threads all waiting on a single condition, a single wait queue, for multiple condition expressions. And we'll talk about that more later. It's very bizarre. And that's one reason why they moved away from the very simple built-in monitor object abstraction, which has been around in Java since day one, to the more powerful reentrant lock and condition object abstractions that came about a decade later, because it was not an efficient way to write the code. And here's what it looks like typically if you use the simple model for Java built-in monitor objects. You end up having to notify all the threads, not just the ones that care about either taking or putting into the queue. And so it means that everybody has to wake up, and then most of them just turn right around and go back to sleep again. And that's a problem we'll talk about in just a bit, which is called the thundering herd problem. But I'll describe that when we talk about usage considerations here in a second. Okay, so that's the end of the structure and functionality part. We still haven't really talked in detail about the methods that are in the condition object, but we'll do that next.